This limit process is challenging. And in some cases, it's probably even beyond your abilities. So I am going to teach you shortcuts that kind of almost make calculus feel like it's like pre-calculus stuff, but it's not, okay? Everything that we do that's important in this class pretty much is based on this idea of a limit, okay? Okay, so let's go ahead and see if we can move forward. Good. So without calculus, for example, if I gave you some function here, f of x, and I said, hey, what is the value of that function at c? Could you do that? Of course you could, right? That's no problem. You just plug c into the function and get the answer out. With calculus, though, we can talk about the limit of a function as we approach c. And you might think, well, Mr. Allen, why would we want to do that? Again, you just kind of have to wait to see what that involves. But basically, everything in terms of derivatives and integrals is a limit. Without calculus, you can find the slope of a line. With calculus, we can find the slope of a curve. This is a very important idea. In fact, it's one of the two big ideas for this lesson, section 1.1. One of the ideas is, how do you find the slope of a tangent line to a curve? You cannot do it without calculus. Without calculus, this problem was unsolved. Okay? We can do secant lines to curves without calculus. Tangent lines to curves, though, we need calculus. We can calculate the average rate of change between two cars. We know that this car is here at time t equals 0. We know that the car is over here at time t equals, let's say, 5 minutes. We could calculate the average rate of change of that car. It's just the slope formula. Calculus, I can tell you the exact speed of the car at any time t that you give me. You cannot do that without calculus. I'm going to skip this next one here. Yay, that's working. More of the same. Let's skip that. Now let's get into, these are now, by the way, the last slide was basically derivatives. Now we're looking at something called integrals, which I have taught you guys about. We actually won't even look at integrals until December, hopefully. Anyways, you guys could find the area of this rectangle, right? No problem. How would you find the area under this curve? With calculus. Okay. And that's a really fun lesson. I can't wait to teach it to you, but that's several months down the road. You could find the center of this rectangle by drawing the diagonals. You could even do it geometrically, right? How would you find the centroid of a region like this under some curve, some arbitrary curve? You got to have calculus. You can find the length of this segment. Oh, it's 5 centimeters. How do you find the length of a curve? Arc length. That's calculus. We will do this too. You guys know the volume of a cylinder. Do you know the volume of a cylinder? Anybody know the volume of a cylinder? What's the formula? Volume equals, it's really easy. What's the base shape? Circle. So what's the area of a circle?
2 pi r.
No, pi r squared.
Times height.
Correct. Now you should know that, but if you don't, I'll remind you from time to time. That's a pretty easy one to remember, right? Once we go over. I'm not saying you knew it right then, but now that I said it, you're like, oh yeah, I feel like I said it. How do you find the volume of that guy? Or the surface? Oh, I guess these are surface areas. It actually doesn't matter if we're talking about surface area or volume. You can do this one without calculus. You can do this one without calculus. Both of these, you have to have calculus. Can you see that calculus might be useful?
Yes.
Everything in our world isn't a perfect cylinder. In fact, most things aren't. Okay. All right. So tangent line problem. I'm going to kind of skip through this a little bit. I want to get to, oh, there we go. Yikes, looky there. Yeah, so here is the kind of more the algebraic idea. So let's say you're trying to find the slope of the tangent line right here. Let's see if I can draw it. Oh, that's not too bad. So you see how that pretend that's a tangent line. What's the blue line?
It's the secant.
It's the secant line. How do we find the tangent line equation? Well, we have to do this limiting process, and the limiting process involves this. It's different. It's a difference quotient. And in fact, in order to find the exact value, this is for the slope of the secant line. How do we find the slope of the tangent line? Well, it's basically this, but guess what we have to stick in front of it? And what part of calculus?
Limits.
You have to do a limit.
Ah,
That'll be chapter 2.
I agree.
Anyway, so what you're doing here is you're taking this secant line and you're pulling this point here closer and closer and closer to, and almost, but not quite, infinitesimally close to that point, and you'll get the tangent line. That's a calculus problem. Another calculus problem is the area problem. How do you find the area under this curve? Well, here's the idea. I could draw 4 rectangles under that curve, couldn't I? Now, would you agree if I took the area of this rectangle, which we all know the area of a rectangle, and this one and this one and this one, and added them all up together, I would get some number, right? Would that be the exact area under that curve?
No.
Nope. Okay. So what if instead of 4 rectangles, what if I did 8 rectangles?
That would give you better.
It'd give me a better estimate, wouldn't it?
Yeah.
What if I did 1,000,000 rectangles?
That would give you the area.
That'd be even better. What if I did infinitely many rectangles?
That's a lot of rectangles.
That gives me the exact answer. That's calculus. Do you guys get a sense of that? Okay, good. I think I want to go there. So that's section 1.1. And I'm just going to tell you right now, section 1.1 is the least of my concerns. You might even say, why did you even show it to us? Well, I just showed you some things. I just planted a little bit of seed in your head. And my hope is that down the road, when I revisit those things, you're going to go, oh yeah, I remember when he was talking about that. And I had no idea what he was talking about. And then hopefully you'll start understanding it. In fact, let me just say this right now. I'm going to pause this. Okay, so this is section 1.2. Notice I put optional here, the delta epsilon definition of limits. We'll talk about that if we have time. The big idea, though, is using the numeric and graphic approaches. Those are the 2 ways of estimating limits. So here's that different quotient thing I mentioned again. So how do we find the slope of this tangent line? Well, remember I said it's that difference quotient with a limit in front of it? Oops. That's actually the formal definition of something called the derivative. We will do that in chapter 2. Actually, you'll do that. Remember I was talking about the area of that curve? There's the formula for that. It looks scary, doesn't it? It's got a limit here. Got some summation. Did you guys do summation in pre-calc? Hopefully.
Yeah, a
little bit. There's a function evaluated at some value c sub I, and then here's some delta x's. That's an integral. So let me tell you this. Guys, I'm a newbie here. Sorry, I'm learning how to use this board. Calculus is based on 3 things: limits, derivatives, and integrals. Everything I will do in this class is basically involving those 3 things for this entire year. If you take Calc BC next year, everything I do next year will involve those 3 things. Everything. Just 3 things. This is chapter 1. This is what we're focusing on now. And guess what these 2 guys require? Limits. So this is, if you will, the foundation for calculus. And it's kind of interesting. We spend the least amount of time on this. But anyways, and by the way, there's the 2 big ideas. This is the tangent line problem, and this is the area problem, area under curve. Okay. Okay, so let me start off by saying this. Most of the time, if you're asked to find the limit of a function, if it was a real life situation, guess what you would do? You see this curve right here? This is the function f of x equals x. That function's a nice continuous function, correct? If I said, what is the limit of this function as f approaches, or as x approaches 2, what would your answer be?
2.
It'd be 2, right? If I had ants going to 2 and ants over here going to 2, where do they appear to be going? What y value? 2. Most of the time, Limit is just the value of the function most of the time. In fact, let's just leave that one. We'll go to another example in a second. How many points are on this line?
A million.
A lot. Infinitely many of them, right? I'm telling you that any value of C that we put in here, the answer is just that value. It's very important for me to start off with that conversation because if I don't do that, you will end up missing stuff. You'll make stuff harder than it needs to be when you don't need to make it hard. Okay? Okay, so here we've got another function. It says evaluate this function, blah, blah, blah. And what am I supposed to do here? Okay, so I'm assuming that this might be a numeric. Let me make sure. Okay, good. Do you have your graphing calculator handy? If you don't, have you guys ever heard of Wabbit?
Yeah.
Okay. Let me go ahead and get Wabbit going here on my computer. I'm going to keep for now. Yes. Good. I feel like it's popped up somewhere, but I don't see it. Can you guys see that little icon at the bottom? Screen is not showing. Oh, boy. Okay. Where's Wabbit, folks? Let me try that again. Right. I do not see Wabbit. Do you guys see Wabbit? Okay, so that's embarrassing. All right, I can't get Wabbit to come up, so I apologize. It worked last week, but now it's not working. So we're going to go from current slide. So what I want you to do is I want you to plug this function right here. Let's see if I can get my ink going again. Plug this function right here into your calculator, please. I was going to show you on the screen, but I apparently cannot do that. If you don't have your calculator, use Desmos or something like that, I guess. And once you get it plugged into your calculator, I want you to graph it. And then once you've got it graphed, I want you to write down the word for the graph of what you have. What is, if you had to use a word to describe what you have, what would that word be? Nope. Hold that thought. You're ahead of me here. You're a little bit ahead of everyone, Dagan. So, what does the graph of this function look like? Line. It looks like a line. Would you guys agree it looks like a line?
Yeah.
Did you graph a line? In fact, I want you to look very carefully on your graphing calculator. Does it look like there's any holes? Now, Dagan already knows that there's a hole on this. Does it look like there's a hole?
No.
It doesn't. In fact, if you go into the table, and this is where I really should be showing you how to do this with Wabbit, so I apologize. If you go into your table and you started at 0.95 and you change by 0.05, you'll notice everything's fine until you get to 1. And it's going to say error. Dagan, what would you say the slope of the line is?
Slope of the line.
Slope of the line that you graphed.
Oh, like 1.
Is the slope 1? What's the y-intercept on it?
The y-intercept is, oh man.
Is it 0?
Oh no, it's -2.
-2? Okay. So the graph looks maybe something like this. -2. Slope is 1, you said?
Yeah.
Okay, and we got a problem at 1, right? So I'm going to say, if you were to zoom in, and you guys know how to zoom in on your calculators, right? Zoom in some. You'll actually see that there is a hole right there. But if you don't zoom in, you probably wouldn't even notice it, would you? Okay, so here's the point. This is a very important point, and I'm saying this as a pun, and it's a pun that's important to this problem. The point is, here's my question. What is f of 1? What is f of 1? No. What is f of 1?
Error.
Error is okay answer. What's a better answer?
D&E.
D and E is a better answer. If you told me, if I gave you this function and I said, you asked me any value of x, you give me any value of x, I'll give you a y value. If I said, what is the value of that function at 1? Your answer should be, does not exist. Now, guys, please don't say error. That's the calculator saying, I can't do it. Okay, does that make sense? There's actually a hole right there. Did you know that? Now, you should know that from Algebra 2. Yes?
Could you also say no solution?
Sure, yeah. It's okay with me. If you said error, I would understand, but I think D and E is better. No solution would be like the solution to an equation. We're not really asking for a solution to an equation. But you're right. If you said that on a quiz or test, I wouldn't mark it wrong, okay? I would say it doesn't exist. Would you guys agree that point does not exist?
Yeah.
Now, here's a more important question. What is the limit as x goes to 1 of f of x? No, it's not 1.
-1.
It's -1. Now, why is it -1? Well, you guys tell me. What y values does that appear to be going to?
-1.
-1. So let me make sure you understand. The function didn't exist there, but the limit does. If I had ants crawling along this line, going to 1, remember 1 is the y value, or I'm sorry, 1 is the x value, and I'm going to call it c. C equals 1. And if I had ants over here crawling to 1 from this side, from both sides, what y value do they appear to be going to? They both appear to be going to -1. That's what we call a limit. Okay? If this side was going to some other value besides -1, like let's say these were all -5s, let's say, then the limit would be does not exist. Does that make sense?
Yes.
This is the numeric method. I used numbers to make that determination. Yes.
Why wouldn't they be going to -2? Is it because the hole's there, or is it?
Why wouldn't they be going to -2?
Yeah. 'Cause
Can you tell me where you're getting the 2?
Yeah, isn't that where the hole's supposed to be? Like that's where they're coming to, like where the hole is.
Okay, so here's what I'd say. Where around what x values are we talking about? What are all these numbers close to?
1.
They're close to 1. So we're talking about when x is 1, right?
Yeah.
Where are all the y values around that? -1.
Okay, so are we not talking about the one on our graph?
I don't know. Maybe I got the wrong thing. Did you do?
I don't know.
Do I have the wrong numbers on here? Okay. You may have plugged it in incorrectly. I don't know.
Oh no. Okay, yeah, I see it.
Okay.
Okay, I was
That's
thinking
okay.
about.
It's okay.
Yeah.
Don't worry. Listen, guys, if you think I screwed something up, let me know because I do screw stuff up occasionally, and I apologize in advance for that.
Personally, I was thinking of the y-intercept.
Now let me make another quick distinction. This was the numeric method, right? What was it over here when I was just looking at the graph?
That's the graph.
That's the graphic method. I know, right? Isn't that silly?
Yep.
But I'm telling you, on the AP exam and on my quizzes and tests, I might give you a picture like this and say, what's the limit as x goes to 1? Now let me give you an easier, let me go back to this one we did earlier. What if I said, what's the limit as x goes to 5 here? And let's pretend that there was still a hole. Let's say there was a hole right there. But I asked you with a limit at 5.
Would it be 5?
It's still 5. But guys, am I going to ask you a lot of questions like this?
No, I got it.
No, but I'll probably ask one every once in a while just to make sure you know what you're talking about. Does that make sense? We're more interested in things like this when we have issues. So, are we okay on that example? Any comments or questions? If you have a question, the nice thing is we're a very small class right now, so you guys got my undivided attention. Okay, So there's the graphic solution. Oh, by the way, here, oh, I think actually I did this. So this is good. I actually took screenshots. Sorry, I forgot that I did this. By the way, I had this module planned out 2 weeks ago. Last week I worked on your next week's module, and now this week I'm going to work on the module after that one. And so if it seems like I don't know what I'm doing, it's probably just because I've done other stuff since then. Okay. So here was the original graph, right? And that's what Dagan, I was asking, what's the y-intercept and all that stuff. Here I zoomed in. And the reason I zoomed in is if you look very carefully, you can see there is a hole there. Now, technically, I want you to think about this. Now, I'm going to ask you a geometry question. What is the size of a point? What is the size of a point?
Trick question.
It is a trick question. Why?
Because it's infinitely small.
Because it has no size. So, and this is the part that's going to be worrisome for you. Technically, if I could show you the line, which actually I can't because all the points that make up the line are not visible, would you even be able to see that there was a hole?
No.
So there's a little bit of faith going on here when we do this math stuff, even though we like to think of math as this black and white thing that's really clear or not clear. You wouldn't actually be able to see. But the graphing calculator is smart enough to know, oh, there's a hole in that spot. But if we went back over here, you would not see that hole if you were zoomed out. Okay, so you got to be careful, and I will ask questions like this on the assessment to make sure you know what you're doing. Okay, so I'm going to go through that. Okay, so here are some non-existent things which we talked about. We went over that on the warm-up. I'm not going to go over that again, but I do want to show you some pictures. Okay, so for example, this is the function. Okay, this is the function. Here is the graph of that function. If I asked you what the limit is, and by the way, this is the notation, as x goes to, let's just say 1. Is this f of x? Okay, good. What's the limit as x goes to 1 of this function? Raise your hand if you can tell me. If you had to predict where the answer going, where are they going? If I said when x is going to 1, what would the answer be?
Doesn't exist.
Incorrect. When x is going to 1, it's 1. Remember, 1's over here. Are there any problems there on the graph? Nope. If I were ants getting really close to 1 from the left or really close from the right, where are they going? 1. Got it? However, what if, so this one is 1. What if, though, I said, what is the limit as x goes to, not 1, let's do 0. What's that one?
No.
That's D and E. That's D and E because now if I have ants getting close to 0 from the left, they're going down there, right?
Yeah.
Correct, I should probably say. If they're up here, where are they going? Oh, they're going to 1. That's different numbers. The ants down here were going to -1 as they get closer to 0. Up here, they're going to +1 as they get closer to 0. That's the example of going to 2 different values. So this limit is D and E. Now, do you understand the difference between the two, though? In fact, the limit exists on this function for almost everything. Pick a number besides 0.
9.
Guess what the limit is? It's 1. What about 1,000,000? What's the limit?
Also 1.
1. What about 1,000,000,000,000?
Also
1. What about pi?
Also 1.
Okay, trick question. What about negative pi?
Oh, it's -1.
-1. Now we're down here, right?
Yes.
What about 0?
Does not exist.
That's the only one that doesn't exist. Being in class is a good thing, right? Being in class is a good thing. No offense to you guys watching on the video. By the way, I'm going to try to record at least one lesson that I do in class as well and post that. I'm going to skip that because I think that's what we just did. Let's see what else we got. Oh, yeah, here's delta. Let's stop on that. Okay.